Hello and welcome to week 9 on energy transfer. Before we push on, I just want to say sorry for last week for not putting the questions up, but it's getting used to doing these videos, I suppose. And I just want to highlight some awesome work from last week. You can see that they're doing everything we asked for. They've even boxed up the element beryllium there, and you've got the element symbol, you've got your mass number, your atomic number, and then from this, then you can see that they clearly understand what's going on, and that is represented by the electron configuration there. So some really good work, neat work. Presented like that in an exam, you're looking at full marks. So brilliant work there. So energy transfer, keywords: useful, wasted, transferred. Your core knowledge questions are: give the units for the following quantities. So we've got time, distance, speed, and energy. And then we got some round in there, bit of maths. Round to 1 decimal place, very handy to have this skill. Off you go. All right then, so time is in seconds, distance is in meters, speed meters per second, not miles per second, or miles per hour, sorry, I should say. Meters per second is what we use in physics, and your energy is measured in joules. Your challenge here to round these up, so 1.5, well, I'm not going to give you a lesson in rounding today. This is just a bit of a recap on your numeracy skills. But if the number next to this number, because we want it 1 decimal place, if the number next to it, to the right-hand side, is bigger, or is 5 or bigger, then this number goes up. So 1.56 becomes 1.6, 24.09 becomes 24.1, 652.1 becomes 2 because 6 is bigger than 5. Again, this 3 becomes a 4 because 6 is bigger than 5. And then 99.01, well, 1's not bigger than 5, so it just remains at a 0. Your lesson objectives today are to interpret Sankey diagrams to be able to calculate the energy transfers in appliance. And if you're year 9 and 10, I would like you to even go on and calculate the efficiency, which I'll obviously show you in this video. Keywords we've talked: useful, wasted, and transferred. And this is linked with your physics. So just to recap on the 8 types of energies. Okay, these are not going to be new to you. We've got thermal, which is heat, really thermal. Electrical, elastic, gravitational. Kinetic, which is a science word for movement. Light, sound, and chemical. And a good way to remember these, because even sometimes I forget 1 or 2. The extreme English geeks know lovely smart children. So I'm not going to spend too much time on this, but you can see that each starting letter is the starting letter of the energy. So it's a mnemonic. It's a simple way to remember. The extreme English geeks know lovely smart children. So if you get an energy question in the exam, just pencil that down, and you know you're looking at your eight types of energy there. So just to recap on energy transfer, we've got a torch. Okay, what's the job of a torch? It's to see in the dark. But there's energy goes into that torch, so we need to put something into that torch to make it work. And these are batteries. You'd be forgiven for thinking that this is electrical energy, but it's not. It's chemical energy is a battery, so energy in is your chemical. And then we've got a couple of energies coming out. One is wasted and one is useful. Okay, so the useful energy in a torch is light. And the wasted energy, well, if you leave a torch on for too long, it's going to get warm, so heat, which is thermal. Thermal is my wasted energy there. And that's about it for a torch. A torch is pretty simple for energy transfer. You've got your batteries, chemical going in, energy coming out is light, and then your thermal. Let's try some of these together. So we've got electric heater there. Electric heater suggests that energy goes in is electric, or electrical. So we've got to plug it in. Energy out, well, it's a heater, so we want heat from it, which we call thermal. And that's going to be our useful energy. I'm just going to underline useful energy. But we've also got other energies coming from that. If you look inside, you might see a filament, what you see in your toasters. Okay, so you get light. It's going to light up. Well, light is not a useful energy for the heater. We don't really want the heater to light up the room. So that's going to be a wasted energy, so I'm not going to underline that. You might get a bit of sound as well. You might be able to hear the heater is on, so you might get sound as a wasted energy. You don't really want that energy. We've got a gas hob here to warm your beans. What's the useful energy? Well, you already know. It's going to be heat. I nearly wrote heat then. It's going to be thermal. Thermal. That's your useful energy. What's the energy that we don't want? Light. Unless you want to light up your kitchen with the stove. I can't see that though. And you're going to be able to hear it's on as well. So sound is another wasted energy. What energy goes in? It's gas. So that's chemical. Slingshot. The extreme English, so E, elastic, goes in. But at any point, you just press pause if you want to do these on your own mind. Energy out, what comes out of it? What's the purpose of a slingshot? Is to move things through the air. So it's going to be kinetic. You're going to be able to hear that a slingshot has taken effect, so that's going to be sound. And if you keep stretching an elastic band, it's going to get warm, so you're going to get some plus thermal. That's about it for a slingshot. And this last one, a waterfall. Well, waterfall falls because of gravity, so gravity is going to go in. Gravitational, I'm just going to put gravity there. The energy that comes out while the water moves, so it's kinetic. Lots of wasted energy. Well, I mean, I guess the purpose of a waterfall is to move the water down. But when we talk about wasted energies, then you see you're going to be able to hear it. There's going to be some sort of heat, so thermal. You'll see that these are popping up all the time. This sound and thermal are common wasted energies there. And, you know, like I said, it's just a recap. I'm going to let you do one. Here it is. Look, test yourself, press pause, name the energy transfers in a car. All right then, so name the energy transfers in a car. Well, I've said that the energy goes in is chemical, which is petrol. And obviously you've got a battery in the car as well, which is chemical. But that battery is sort of powered by the movement, really, the kinetic energy. But we're going to keep things simple. So petrol goes in, chemical. Energy that comes out, the useful energy there is kinetic, because the car's moving. And if it's dark, you might need a bit of light. So I'm just going to underline those as useful energies. The wasted energies, unless you like showing off for a car like this, you might want to rev your motor a few times. So sound is a wasted energy, really. And if you can think of any more, leave them in the comments, okay? But there's going to be one more there at least, which would be nice if you left there as a comment there. And I've already alluded to these are the ones that are common, okay? So I've missed one off there on purpose. So, conservation of energy. Well, energy, it can't be created or destroyed, okay? You can't just make energy. It doesn't just happen. It gets transferred from one to the other. So the statement there, energy can't be created or destroyed, only transferred from one type to another, is something that's common in exams that for you to give as a 2-mark answer. It'll say, give the conservation of energy, okay? So you just got to know that it can't be made. Energy can't be made. It's just transferred. So when I'm talking to you now, the energy really comes from chemical energy. I've had my breakfast and I'm using my muscles, kinetic. I'm moving my muscles to project sound. So it's not just sound energy I'm making up. It's coming from, you know, I'm burning calories. I should keep talking, shouldn't I? I'm burning calories whilst talking to you. So it's taking energy for me to talk to you. So you can't just create any energy. And the input energy must always equal the output energy. And we'll see now. Yeah, I'll just leave it there. So the input energy must always equal the output energy. So we got some problems here. I'm going to do the first one with you and then we start doing them together. So problem one is television. And it's laid out like this. So you've got the energy, the input energy is 120 kilojoules. Kilojoules, by the way, the K just stands for 1,000. So if you've got a meter and then a kilometer, it's just 1,000 meters. So don't get put off by this kilojoule. And then you can just about see that. That's a K there. I promise you it is a K. I've made a mistake, I did. And I just put joules, but it is a kilojoule there. So the output energy, so you've got a useful energy of light, because you need to see the TV. You're going to have a useful energy of sound, because you need to hear the TV. But you also got this heating. That should be thermal there, but I've taken this from somewhere else. And that's 100 kilojoules. So when I say the input energy always equals the output energy, you can now start to work out the energies involved here. And I've got this bit of a success criteria here. You can see that energy can't be created or destroyed. Input must always equal output. And we're going to get onto that challenge for year 9 and 10 in a second now. So let's just identify the energies. So the input energy is electrical. Okay. And it is 120 kilojoules. You've got the output energy, you've got light, which is 15 kilojoules. And you've got thermal, which is 100 kilojoules. And it wants to know, look, it's a blank space there for sound. So what is sound energy going to be? Well, if we've got a total of 120 going in, this must always equal whatever's coming out. So what have we got coming out? We've got 100 plus 15 plus the sound energy, okay, which I don't know, but I can work out because I know 100 plus 15 plus something is going to give me 120 kilojoules, and that something must be 5. Okay, so 100 plus 15 is 115. How do I get that to 100? You could essentially say 120 minus 115 there is going to give me 5 kilojoules. That's my missing energy. I'm going to do some practice on this. If you're year 7 and 8, you can have a go at this by all means, but don't get too bogged down if you don't get this. I'm going to try and work out the efficiency of this appliance now, this television. So the formula for efficiency is efficiency. So how good is this TV at doing its job? How good is it at producing the useful energy? So the efficiency equals the useful energy over the total. And that, because it's a percentage, we're going to times that by 100. So if we look at our useful energy in this one, we got light is a useful energy of a TV because you need to see the picture, and we got sound, so we want light plus sound. Well, I've got 15 plus my 5 sound there, so that's going to be, let's try and find some room here. It's going to be 20, so 15 plus 5 is 20, over my total energy is 120, because that's the energy going in, 120, and then times 100 to make it come out. That's going to come out as 16%. I'd encourage you to do that on a calculator just to check me there, but it does come out as 16%. So you just, in the calculator, 20 divided by 120 is going to come out to 0.16, and then when you times it by 100, it's going to be 16%. So 16% efficient. That means that TV is not very efficient at all, because it's only giving you 16% of the energy that's going in. There's only 16% of it is useful. Okay, let's try another problem. So I've got my success criteria here. I've got the input energy. Well, my input energy is electricity, so I'm not going to write electricity down at this time. I'm just going to put E equals 300 kilojoules. Okay. And then my output energy. Now I'm going to start dividing these up into useful and wasted now, because it helps me when I come to my challenge. So a hairdryer. Well, you've got a fan inside a hairdryer that moves. So that is a useful energy. So the movement, or kinetic we're going to call it, is 50 kilojoules. And the heating obviously dries your hair. So thermal is 240 kilojoules. That's a useful energy. Sound doesn't really dry your hair, so I'm going to put sound over here. Well, we don't know what it is, but we know that energy before must equal energy after. So my energy before is 300, is going to equal 240 plus 50 plus something. Well, hopefully you can see that that is 10, because 240 plus 50 is 290. To make it 300, we need 10 more. So my sound is going to be 10 kilojoules. Okay, so I'm going to put 10 there. Again, you could look at it. You could add these. No, we won't even go there. Okay, it's such a simple calculation that we shouldn't need to go over this. So we've done the first bit, and then year 9 and 10, then onto the challenge. Calculate efficiency. So we got percentage equals, it's going to be your useful over your total times 100. So what's my useful energy? My useful energy is kinetic and my thermal, which is 240 plus 50, which is 290, over my total, which is 300. You can see here that I've got, well, I can see already from this large number on top. Even, by the way, your number on top is never going to be bigger than the number on the bottom because it's a percentage. Okay, so, but it's still a big number there. So this is going to be really efficient. I'm just going to use my calculator now. So 290 divided by 300 comes out to be 0.96. When I times that by 100, I'm going to come out to be 90. Oops, let me change my pen. It's actually 0.966666. So I'm going to round that to 0.97, which is 97% efficient, which is very efficient. I doubt if these figures are actually correct for the hairdryer. You're going to get a lot more sound energy, I should imagine. Well, I wanted to try this now, see where we're going. Before we move on to the Sankey diagrams, see how you fare. So try it, press pause, see what you come up with. Okay then, so you can see I've got quite a bit going on, so I'm going to run you through this. First of all, I identified my energy, so it says there that it's 1500 watts for 4 minutes. We don't have to worry about that. It comes out to be 3,600 joules. So we're dealing with joules now, so that's 3.6 kilojoules. But we're going to leave it in joules, so my electric energy going in. My output energy, well, my useful energy is the movement, because again, it's kind of like a fan that sucks the dirt and grime in. We've got 500 joules there, and my wasted, well, heat is no longer a useful product, useful energy for me now, and sound is no longer a useful energy. So these are my wasted energies. We didn't know thermal, so what I did was 3,600 must be equal to my output energy, which is 500 plus 100. So I need 3,000 there to take it to 3,600. So my thermal energy is 3,000 joules, or 3 kilojoules. And then for my year 9 and 10, then for my challenge, my percentage equals the useful over total. I should have put equals there. Times 100. So my useful was 500 over the total 3,600 times 100. And it came out to be 14% once I rounded it. So 40% efficient, not very efficient there. So let's take it to the last stage now, which is, we're going to leave that there. We're going to talk about Sankey diagrams. Now, Sankey is a name, so it's always got a capital S. It says there, a diagram that shows how energy is transformed inside a device is called a Sankey diagram. Arrows that continue to travel to the right is always the useful. So if it continues to travel along this line, it's always useful energy. And arrows that go down shows your wasted energy. And more often than not, these are going to be bigger because the thickness of an arrow shows how much energy. And we're going to do this on a grid now, so I'll just show you that. So if you take the thickness of this electrical energy, which is 100 joules going in here, let me just zoom in here. Okay, you can see that the light energy is not that, the line is not that thick there, but the heat energy is very thick. So you've got, it's a 10% efficient, I can see from that, because you've got, if you used to put total on top, 100 on the bottom and 10 on top, it's going to be 10% efficient because you've got 90 joules being wasted there. So anyway, let's have a look at some diagrams. Let's just go through the success criteria in a minute. So each square is going to represent a unit of energy. If you count the squares and then multiply the number of squares by the unit of energy given, you're going to be able to know how much each square is going to be worth. And we'll do that together now. Input energy is always on the left, and the useful energy always goes on the right, and then the wasted energy is down. So we've talked about that. So use your Sankey diagram for a car. So there's a couple of wasted energies here. It's not going to show them. So the input energy is always going to start here on this grid. And I've said there that 1 square equals 10 joules. Well, let's count how many squares there are. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Nice, easy number. So my energy going in is going to be 10 squares times 10 joules, which is 100 joules going in. Okay, so hopefully quite easy so far. Now we look at the useful energy. The useful energy always carries along the top. Well, it's only one square, and it says there 1 square equals 10 joules, so my kinetic energy is going to be 10 joules. Now I'll move on to my wasted energy. I've got 1, 2, 3, 4 squares there. Okay. By the way, it doesn't matter how far it comes across and how far it comes down on the wasted energy. We're only looking at the thickness of the lines. We're not looking at the length of the line, just the thickness. We're dealing with the thickness of the line. So I got 40 joules here, because each square represents 10 joules. And then for my thermal energy, I got 1, 2, 3, 4, 5. I got 50 joules here. And really, all this should add up now. 50 plus 40 plus 10 adds up to 100. And that's how I know this chart is right. So it's just what we've been doing, only a bit more visual. So calculate all the input and output energies. Well, I just did that. Identify the useful energies, the kinetic energy is the useful energy. Calculate the efficiency. Well, we'll do that a bit quick now. So percentage equals useful over total times 100. So the useful energy here is 10, and that's going to be over 100. And that is, if you times that by 100, then that's going to be 10% efficient. You can check on a calculator if you like, but I can promise you that is the correct answer. So let's just push on to problem 2 now, where we've got an electric motor. So 1 square now equals 20 joules. So calculate the input and output energies. Well, it's already given us 400 joules there. So if we count, this is, I can see already that each one of these big boxes contains 10 squares, and I've got 2 of them. So I've got 20 small squares, and if each square is worth 20 joules, then I've got an input energy of 400, because 20 times 20 is 400. Now it's these ones I need to work out now. So my useful energy is gravitational potential. So I got 1, 2, 3, 4, 5 squares there. So that's going to be 5 times 20. That's 100. 100 joules. Okay. Then my wasted energy, I got 1, 2, 3. So 3 times 20 is going to be 60 joules. And then I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times, what was it, 20? Well, 10 times 20 is 200, and then 2 times 20 is 40, so it's going to be 240 joules. Let's make sure that we're okay. So I've got my input always equals output, so I've got 240 plus 60 is 300 plus 100, 400, yes. I'm right, because it all, so this energy equals these energies, okay? Calculate the efficiency, so that's going to be the small, so that's going to be useful on top, which is 100, over my total, which is 400, times 100, so that's going to be a quarter, it's going to be 25%, isn't it? It's a quarter, really. So that's going to be 25%. Use a calculator, by all means, to check yourselves. I want you to try this now, okay? I don't think it's too difficult now you've been shown, and then we'll push on to the assignment. So, Sankey diagram for an iPod here. Okay, do your best, have a go. Okay then, so I've done this for you now. You can see, I mean, it might have been difficult to zoom in on the video, but you had 13 squares here. So let me just zoom in now. So you had 13 squares, and each square was 10 joules. So we had 130 joules here. Now we got 2 useful energies. So we got 1 square, which is 10 joules. We got 3 squares, which is 30 joules. So we've got total useful energy there, because they're moving to the right-hand side, which is 40 joules. And then we got this wasted energy then of 90 joules, 9 squares there. So if we just do the efficiency then, so I forgot to put the percentage equals. So 40 was my useful, 130 is my total, times 100. I'm going to round that up to 31%. So hopefully you're getting this. If not, go back and just watch me do a couple of the examples. Quick quiz now before we move on to the assignment. Again, press pause and see what you're getting right, and just to see if you need to revisit anything. Okay, so name all 8 types of energy, give the energy transfers in a kettle. What is the wasted energy in this kettle? Where would you see the wasted energy represented on a Sankey diagram? And what is the formula for efficiency? Off you go. So the quick quiz answers here. So name all types of energy. I've just done the first letter just to save some time. So thermal, electrical, elastic, gravitational, kinetic, light, sound, chemical. The energy transfers in a kettle where you need to plug it into electricity to get it going. So electrical then converts to thermal, which warms up your water, which is the useful energy. Plus sound is your not very useful to us. I mean, you'd be forgiven for putting other types of, because it does move a little, so you can put kinetic, but I've tried to keep this very simple. Some use light as well, so you could have those as wasted energy. What is the wasted energy in this one, though? This example, the main wasted energy is sound, because you can hear a kettle when it boils. Where would you see the wasted energy represented on a Sankey diagram? Well, the wasted energy goes down, so I've said on the bottom. What is the formula for efficiency? So again, I've been quite lazy and just put percentage there, but you could put efficiency equals useful over total. So the small number over the big number times 100. So we're going to move on to your assignment now, and I'm actually going to give you the questions for the assignment this time, not like last week, just talk about the assignment and then just end the video. So we're going to do this in the same way. You're going to do it on a piece of paper, you're going to take a photo, you just upload it. It's way easier than downloading worksheets and opening PowerPoints. So you're going to complete on a piece of paper, a photograph, use the layout that I've shown you. So I wanted to be very clear on the total energies and the wasted energies and the useful energies and you know, what each energy's value is, and especially when it comes to efficiency, then try and give me, and instead of just giving me a number like 99% efficient, try and give me the whole equation. There's going to be 4 questions. Year 9 and 10, I want you to calculate the efficiency. Year 7s and 8, you can have a go if you want as well, it's not going to harm. So here's question 1. Here's question 2. Here's question 3. Here's question 4.